Started. All right, so welcome to tonight's segment of the faculty lecture series. For those of you who do not know who I am, I'm Jessica Lahiri, professor and director, and I coordinate the lecture series. So thanks for attending tonight's lecture. Keep an eye out for upcoming lectures, not next week because there is a university break, but the week after, Thursday, October 17th, Dr. Colin Ryall of History will be giving the next lecture. So this evening's lecture is presented by Dr. Chayan Lahiri, Assistant Professor of Geosciences from the School of Science, Technology, Engineering, and Mathematics. Dr. Lahiri was born and raised in Kolkata, India. Then he moved to the US in 2006 for graduate school. Dr. Lahiri earned his master's and PhD in hydrogeology from the Universities of Idaho and Mississippi, respectively. He loves to eat and cook, read, teach, hike, and take pictures of geological features, and he also loves dogs. So tonight's lecture is titled Alluvial Fans, Importance in the Climatic and Landscape Controls on the Forms They Take. And in his words, this lecture will introduce the audience to alluvial fans, fan-shaped landforms created when streams deposit sediment at the base of mountain ranges, canyon walls, or hills where streams' gradients undergo a sudden change. The presentation will also focus on the importance of these landforms and how variations in the landscape and climate influence their formation. So, please help me in welcoming Dr. Lahiri.
Thank you for coming this evening, making the time to come this evening. Again, my name is Chayan Lahiri. I'm going to talk to you about alluvial fans this evening. And the title slide here has an alluvial fan. And I'm not sure how many of you are aware of what alluvial fans are. So let me just point out on the slide what I mean by an alluvial fan. So it's this feature that is fanning out from the mountain front. And this is a picture I took of, this is the Blanca Creek alluvial fan, and I'll point this out in maps as we progress through this, the talk. I took this picture a couple of years ago from Highway 160, and you can see several fans as you're driving towards the sand dunes, as well as towards the town of Blanca. Before I start, I would like to acknowledge a few things. I'd like to acknowledge my parents and my family for the love and the guidance and the care that they've given me over the years. I wouldn't be here without that. I would also like to thank my colleagues, Tim and Liz, for giving me the opportunity to work with them. They work with the US Geologic Survey. This work gives me the opportunity to stay up to date in my field. More importantly, it gives me the opportunity to generate information for my students, because this gives me the chance to add some of the stuff that's coming out of these research projects to my classes. And the students are not just exposed to the textbook, but information that is more current. So I'm very thankful for that opportunity. I'm also going to acknowledge some of the data resources that I will be using, and I use these very often in my work and my teaching. These are mostly freely available, so during the course of the presentation, if any of these resources interest you, I'll be happy to share information about it or them with you after the talk or later on. Because you can use a lot of this even if you're not a geologist. You don't need to be a geologist to use some of the resources, the freely available resources that I use. What I'm going to do first is I'm going to outline or present an outline for the talk. There are three sections that the talk is divided into. We'll start by defining what alluvial fans are, and then we'll move on to how they're formed. In section 2, we'll talk about the importance of alluvial fans, and then in the last section, we'll talk about the landscape and the climatic controls that are exerted on fans to change the shape or the characteristics that they have in different regions. Okay, so let's start with the first part, which is defining what an alluvial fan is. And what I'll do is I'll provide a very simple definition to start. An alluvial fan is a depositional landform. For the benefit of folks who have not had any experience with geology, I would like to define these two terms, words, depositional and landform, in order to create a better understanding as we go forward. So let's start with the word landform. What does the word landform mean? So a landform is a feature on the Earth's surface, any feature. The definition here provides includes mountains, valleys, plains, plateaus. All of these are landforms. I have a cartoon here which provides you with additional landforms, things like cliffs, canyons, coastlines, etc. So these are all different types of landforms. You can characterize or classify landforms based on the way they are formed, the geologic process that forms these landforms. And so, for example, a cape, a coastline, a continental shelf, these are all coastal landforms because they're created by coastal processes. So what we're going to do in the next 3 slides is we are going to look at some other landforms other than alluvial fans to develop this understanding a little better. So these are volcanic landforms. These are 2 extinct volcanoes here in the valley. This is San Antonio Mountain and Los Mogotes. These are 2 extinct volcanoes. So since they're created by volcanic processes, they are volcanic landforms. And I took this picture from, just in case if you're interested, from the Walmart parking lot. You can see these landforms from there. This is a valley. This is an erosional landform. It's because it's called an erosional landform, or it's categorized as an erosional landform because this feature is created by the process of erosion. This is Black Canyon, not the Black Canyon of the Gunnison, but this is Black Canyon just north of the Orient Land Trust. This is a depositional landform. This is a much smaller landform than what we've been looking at so far. This is about 5 feet across. This is a talus cone. A talus cone is a depositional landform because it's this cone-shaped feature that's created by sediments that have been deposited at the base of the slope as they come down the side of the hill. And it's very similar to a alluvial fan, A, because it's a depositional landform, but B, because it's also very similarly shaped. The only difference is this is created entirely under the action of gravity. There's no water involved here. Alluvial fans are formed under the influence of water. So as water is moving sediments, it deposits and creates the fan. So with this information, let's just get back to the topic, which is alluvial fans. And I'm going to provide a more detailed definition. We already know it's a depositional landform. Let me provide a little more detail to it. And in this definition, we'll also be able to define it in more detail. We'll also be able to see how it's formed. Excuse me. So this is a stream that's coming out of a confinement. The confinement could be a canyon, it could be a valley, it could be a hill. That water is flowing through the valley of a hill or a canyon or a mountain valley. And as it's moving through this confinement, this is referred to as the catchment area. It's eroding sediments out as it's moving. As the water is flowing, it's eroding sediments out. And when it reaches the point where, this point, which is where it opens out into the valley, two things happen. A, it begins to slow down, the water begins to slow down because the slope has reduced. And B, it has more space to spread out. So these two things are happening simultaneously, as a result of which this stream begins to spread out and do what you see here. And in the process of doing that, it begins to deposit sediments. So that is this is an example of an alluvial fan. It just fans out and slows down and deposits sediments. What's important to note here is that as it's depositing sediments, it's depositing the coarsest grains or the largest sediments at the highest point in the fan. And lower down towards the toe, you get finer sediments. So it grades sediments from coarser to finer, because the water, when it's exiting the valley, it's moving the fastest and the slowest at the toe of the fan. So that's where it deposits the finer sediments. Now, the highest point in the fan is referred to as the apex of the fan. And the proximal end is where the coarser sediments deposit. And the distal end, or the toe end of the fan, is where you have finer sediments. Now, what I'm going to do next is I'm going to show you a video that I took that I recorded on the stream table here on campus. So this should give you an idea of how just should. So this is the water is flowing through this confined channel at this point, and this is where it would emerge from confinement. The valley wall will end at this point, and you'll notice that as that's happening, sediments are going to that it's picking up. The channel is picking up higher up. It's picking that stuff up and it's moving down, and it slowly is depositing stuff. What is important to note here is that at this point, this channel is active. As time goes by, this channel will get overwhelmed with sediment and it will move a valse to elsewhere. And this process is going to continue, and more sediments are going to get deposited, and the fan is going to build up. So this is, again, why I'm referring to this as a depositional landform. It's depositing sediment. It's important to note here that this fan-like feature was created in a minute. It's not this fast. Fans form over many decades, centuries, or even thousands of years. So let's just want to point that out, that there's a huge difference in the temporal scale of what we just saw and what happens in natural systems. So I'm going to now show you some fans here in the valley. So this is Highway 150 that goes to the sand dunes, and here is an apron of fans that have formed all along the mountain front. This is the fan that we saw in the title slide. This is the fan that comes out of the Blanca. This is the Blanca Creek alluvial fan. So this apron is referred to as a bahada. A bahada is an apron of fans that have been created in this area. So let's look at these fans from the west. Let's take a western view. Let's view it from the west to see them a little better. So here are, again, these are the fans all along the mountain front. Some of the work that I'm going to cite and some of the understanding that I've developed comes from Nikovic 2020. This is a dissertation that was published. She was a student at Montana State University, and she worked on these fans. So what I'm going to do is I'm going to first outline the catchment area of one of the fans that I've done some field work on, and we're going to use that fan as we go forward. So here is the catchment area for the Hallbrook Creek fan. The catchment area, just to remind ourselves is the area where sediments are being picked up by the stream. And this is also an erosional landform. It's the valley. And it's depositing sediment in this feature here, which is our alluvial fan. That is the approximate boundary of the fan. And we've got the apex of the fan, that's the topmost part of the fan, the proximal and the distal end. So you go from bouldery to sandy sediments as you go from the top to the bottom. A few things to note here as we go forward. You'll notice that every one of these fans have a lot of channels that are coming out of the top of the fan. Every one of them have channels. Also, you'll notice that this trail goes up to the top. So if you have a chance, if you drive up the trail, you'll see that the trail itself is going to get from being sandy to bouldery. And you can actually see that when you go up to Zapata Falls. As you go up the trail in Zapata Falls, you'll probably be able to see the same. Not probably, you will see the same. Okay, so what I'm going to show you next is some pictures that I took while I was helping a student do his capstone project next. So here is the bouldery proximal end of the fan. So you can see how large these pebbles are, these boulders are. And this is at the top end of the fan. This is Michael Shuba. He graduated last year. This picture was taken in the summer of 22. He wanted to start his capstone project before he actually enrolled in capstone, so I helped him collect data. This is Michael's son, Jaden. We took this picture at the proximal end. Again, you can see a very large class, and which is floating in this sandy matrix. But it's very, the clasts are very large, they're boulders. If we look at the southern, the lower end of the fan, you'll notice that here there are no boulders. This is the distal end. This is very sandy. So the boulders have now transitioned in the lower end, they've transitioned to sand. So you go from coarse at the apex to finer towards the toe. This, by the way, is Quincy McDonald. He was also working with us that summer. He actually took the previous picture, so he was not in that previous picture. Okay, so let's look at what a fan looks like in a topographic map. We've been looking at aerial photographs. This is a topographic map. It's the same fan coming off that catchment that I showed you in the earlier slides. What I've done here is I've just overlaid the topographic map on the Google Earth image. You'll see that a couple of things to note here is that the contours are these concentric contours that define the fan's surface. Because there are fans that wrap their way all around the mountain front, these contours continue on. If it was a standalone fan, it would be a contour that radiates out from this one point. But because they are continuously, there are fans all along the mountain front, these contours continue on. And we'll come back to more examples of contour maps and fans in a later part of the discussion. Another thing to note here is the streams. You can clearly see all the streams that are coming out from the apex of the fan and causing deposition to happen. Okay, so now what we're going to do next is we're going to look at a very large fan here in the valley, which is, I think, if these fans are not very well known, the fan that I'm going to talk about is even more unknown. Maybe, I don't know, maybe you guys know, I don't know. We'll talk about it here in a second. So here is the Holbrook Creek fan that we talked about so far. And here is the Rio Grande fan. This is a very large fan that was formed as the glacial meltwaters were coming out of the Rio Grande and depositing sediment all along here. So if you go out to Del Norte and these areas here, you'll find very large boulders because that's the proximal end of this fan. If you look at these areas just north of Alamosa, you'll find sandy deposits because, again, this is the distal end of the fan. Compare this fan to the size of these fans here. There's a huge difference between. These fans were also created by glacial meltwaters, but the glaciers that were coming out of here were much smaller than the ice field that was formed on the San Juans. Now, one thing to note here before we move forward is that the northern part of the valley is thus flanked by alluvial fans on both sides. You've got the Rio Grande fan and these fans coming off the Sangres on the east and the west. So it flanks this northern part of the valley. This is also where the trough or the closed basin exists. So this is the section which is the closed basin. All the streams coming out of the north end up here in this depression called the sump. And the Rio Grande flows out south and drains the southern part of the valley. Now let's look at this section here, and I'll show you something that I find very interesting. So this is Del Norte, and this is the present day floodplain. This is where the Rio Grande is flowing at present. Look at these features here in these fields. These are relict paleo channels that water was flowing through these areas when the fan was actively depositing during the time that the glacial waters were coming out of the San Juans. So you can still see these areas. Okay, so before we end section 1, I'd like to show you a feature that I took a picture of just next to my driveway. This is from the September 5 last rainstorm. It rained all day. The following day, when I just noticed that there is this feature. There's a little gutter spout here, a drain spout here, that was like releasing a lot of water, and it's obviously higher at this point. It moved sediment downhill, and because of the weeds and the grass and these little pebbles here, there was this confinement that was created, and it was able to confine the sediments to this point, and it then fanned out to create a fan-like feature downhill from this point here. So what is important to note here is that sediments, irrespective of the time scale that they're acting on or the spatial scale that they're acting on, tend to behave in the same way of spreading out and settling down when the speed of, because this is the point where the water slowed down because the slope reduces at this point. So it spreads out and it deposits these larger sediments out here. Okay, so we're now going to get into talking about the importance of alluvial fans. Let's start with something that's very important with all the environmental problems that we're facing at present, which is groundwater recharge and agriculture. So back to our bird's eye view of the valley. Way back, the earliest literature that I've been able to find is Emery, 1972, and he talks about groundwater getting recharged through the fans. Now remember, we've got fans flanking this northern section of the valley. So these areas are where water is coming out of the mountain front and flowing over the bouldery, coarser end of the fan and seeping into the ground. Just to illustrate this better, if you fill a plastic bottle with marbles and make holes at the bottom and pour water through it, it's going to very quickly move through the column because of the spaces that you have in between the marbles. So that's similar to what is happening at these upper levels of the fan, closer to the apex where it's very bouldery. As water is flowing over these sections, it's seeping into the ground and recharging the groundwater. This is a newer publication, Bexfield and Anderholm. They talk about, this is a block diagram that they have in the publication that I modified slightly. And you can see the streams coming out of the San Juans, and as they're flowing over the proximal end of the fan, the blue arrows indicate seepage of water into the subsurface. So groundwater is recharging through the alluvial fans, the proximal end of the fans, definitely. These areas are also where a lot of agriculture is practiced. Now, groundwater recharge is something that is happening not just in these fans, but across the world. Wherever fans exist, wherever you have coarser fans. The same is true for agriculture, because these areas are where streams are constantly bringing in nutrients to enrich the soil, and so it's an area where agriculture is practiced. Also, the proximity to the groundwater is the abundance of groundwater in these areas also help with having agriculture in these areas. Okay, so again, you can see how much agriculture is practiced in this area because of what I just described. I'm not suggesting we've in the valley, here in the valley, as is true for across the world, groundwater levels are falling generally. But I'm just saying here that it's recharging through this area. It's not like that. I'm not suggesting in any way that we don't have groundwater problems. It's just that it's recharging through this area. Okay, so let's go to the second importance, which is dating fault activity. So here is an image. This is a hillshade image. A hillshade is an image that you can create to give you depth perception. It's actually a two-dimensional image, but it gives you a sense of high points and low points in the image. This is the northern, these are the Sangre de Cristo, this is Sangre de Cristo range, and this is the Culebra range. And all along the mountain front, you can see this black line, which is the Sangre de Cristo fault. So that's causing the mountain range to rise. Now let's look at take a closer look at this spot here, which is just the area that we were looking at, the alluvial fans. So here is a zoomed in view. So these are our fans, and you can clearly see that these have these, the fans have drainage areas that are coming out of the fans. This line here, that is the fault scarp. Compare it to here. The fault turns towards the east here, and that's what you see at this point. So why is it important? It's important because the sediments that have been offset by fault activity, if you could date those sediments, you could get an estimate on when the fault moved to cause that offset. So this is something that you could do in any alluvial fan that is created at the base of a mountain, which is a result of faulting. Okay, let's look at another important reason why we should know about fans. It acts as a buffer, a natural buffer to sediments. So here is another example of a fan. This is a fan from Ennis, Montana. This is the town of Ennis. Now this here is the fan, which is coming out of this catchment, and it's spreading out, and what it's doing is it's buffering the sediments that are coming out of the mountain front and preventing all of this to end up in the river and the lake. So it's acting as an agent to prevent all that sediment to reach the open water bodies. This is the topographic map. You can see how these contour lines are radiating from the apex of the fan. That's the apex of the fan. That's where it's exiting the mountain front and depositing this stuff, which would have probably ended up in the stream if it was not trapped here. One last thing before we move on to part 3 is that alluvial fans have a lot of human settlements as well. So a lot of big cities across the world are built on alluvial fans. Salt Lake City is built on an alluvial fan. This whole area is a fan. This is the Great Salt Lake. Let's look at a hillshade image to understand this a little better. So here is our hillshade. Remember, this is that depth perception that we were talking about earlier. This is where Salt Lake City is. And this is the fan, because you can see that these mountains are releasing water through these drainages into these channels, and that's depositing sediment. This whole surface is a alluvial fan. A closer look, this gives you a better idea of this high point is the fan that the city is built on. It's important to know about these because water is flowing through these densely populated areas, and it's important to know which way the water would end up if there are flooding, if there's a situation where a flood could arise. That's the reason why it's important to know. Denver is located on an alluvial fan. Los Angeles is also on an alluvial fan. So it's very important that in these densely populated areas, planners have a good idea on which way the water could be routed or needs to flow to prevent a great deal of damage. All right, so we are done with part 2. Now we're going to move into the last part of the talk, which is on the landscape controls and landscape and climate controls on the shape that alluvial fans take. So back to our Holbrook Creek alluvial fan. We already know that from the top to the bottom, it goes from bouldery to sandy. The relief, the change in elevation from the top of the fan to the bottom is about 2,000 feet. That's primarily because of how much activity there is along the fault that runs approximately north-south in this section. Because why is that important? It's important because as the fault is causing the mountain range to rise higher, the slope in the catchment area is increasing, causing more erosion and more deposition of sediments in this area. So these fans are very tall. A friend of mine who recently passed away, Bob Kirkham, he worked as a geologist for the Colorado Geologic Survey. He mentioned to me that in his experience, these are some of the tallest fans in the world, 2,000 feet of elevation from the top to the bottom. Just to remind ourselves, these are the boulders that we saw earlier. This is the proximal end of the fan, and this is a soil pit that we dug, and you can see how coarse, even the sand is very coarse. It's not fine sand, it's coarse sand, because of how fast the water flows and how much it's depositing stuff. Okay, so now we're going to go to a very far off location from here. So we're going to go to Mississippi. So this is Highway 35 that goes along, it's approximately north-south trending. It's about 80 miles from Memphis. And these two features are alluvial fans. They don't look like alluvial fans, right, based on what we've been seeing so far. The reason why they don't look like alluvial fans is because they're densely vegetated, which is not the case in the fans that we've seen so far. Plus, they're also not as tall. They're underwhelming in comparison to what we've seen so far. So let's look at a topographic map that will reveal whether these are fans or not. So here you've got Stark Hollow, which is a little creek that's coming out of the bluff line, and you see the concentric contours that define the fan that is formed by Stark Hollow. And Murphy Branch is another fan which is going towards the southwest. So these two are alluvial fans. They are very densely vegetated. The top of the fan is sandy and the bottom of the fan is clayey. Compare that to what we saw in Holbrook. We went from bouldery to sandy in Holbrook. Here, it's still maintaining that same characteristic of coarse to fine, but the coarse is sandy at the top, and then we've got clay stuff at the bottom. What is the elevation doing here? If you notice that this is the 150, I don't know whether you can see, but this is the 150-foot contour line, and it's about 200 feet at the top. So the elevation change is only 50 feet. Compare that to what we saw at Holbrook, 2,000 feet. There's a huge difference in elevation in these fans. So what we're going to do next is we're going to go to Tennessee next. This is the area that I have been doing some work in, and compare the fans there to what we've been seeing so far. So this is Reelfoot Creek. This is located in the northwestern part of the state of Tennessee. It's the largest natural lake in Tennessee. This is the Mississippi River, so it's just east of the Mississippi River. And this is the Mississippi Bluff Line. What is interesting to note here is that there is a fault system that runs along the bluff line like so, which is very similar to what we see here in the valley. In the valley too, you've got a fault system that runs along the mountain front. There's a huge difference between this bluff line and the mountains here. But still, there is that common feature of there being a fault system that runs along this high point. What I'm going to do next is show you an outline that I created. This is an apron of fans, which is not visible at this point. I just draw out the line to show you where the fans exist. And what I'm going to show you next is contour lines to show that these are fans. It's an apron of fans that extend from the north to the south over about a 10-mile length. So here is or are the fans. Compare what you see here. You can't see the fans at all here, but look at the fans formed. You can see the contours, the concentric contours, which have been derived from the 2019 data. How high is this fan? Let's look at Reelfoot fan. This is the Reelfoot fan, which is the largest fan in this area. It goes from 300 feet, which is this color here, to 85 feet, 15 feet in elevation. Again, compare this to what we saw in Holbrook and at Stark Hollow in Mississippi. So these are smaller fans, elevation-wise as well. Same characteristic is maintained here. It's sandy at the top and very clayey at the bottom. What I'm interested in, what I'm doing at present, is the evolution of the fans. So here is, these are contour lines derived from the 1925 topographic map. So you'll see that the fan has evolved here. This section, they've done some, they've moved stuff around, moved sediment around in developing the area. But everywhere else, the fans have grown. If you look at what is happening in 25 to 2019, approximately a century of data, that shows you that the fans have generally gotten larger. The reason why that is the case is the bluff line is where there is a lot of clearing of land. They are clearing land for agriculture. That's creating the opportunity to cause more erosion to happen. That's depositing in the fans and getting bigger. It also allows the fans trap the sediment and prevent it from filling up the lake, like we talked about earlier. So the fans are getting bigger over time, and again, it's 15 feet from the top to the bottom, and it goes from sandy to clay. Let's look at some pictures of the fan. This is the fan's surface. Again, compare it to what we saw in Holbrook. Very densely vegetated, very fine-grained, because the landscape itself doesn't have the sediments the similar sediments to deposit on the fan that we saw here in Holbrook. So with that, I'm going to end, and I'll open it up for questions. This is my dog, Dushtu, and I'll be happy to answer questions.
Chayan, can you talk a little bit more about when a city is built on the fan, how that impacts current day deposition?
Well, I didn't talk about this. What they normally do is they make sure that they have a good hold on where the water is flowing through. So if we go back, if you look at this figure here, you'll notice that there's this active channel which they're forcing the water through. If you compare this fan to some of the fans that we've been seeing, there are many more channels along a fan. So what they do is they force the water through one area and control the flow and keep it at that one point so that it doesn't flow out in different directions and cause flooding. So they have a controlled area where they drain the fan.
So in Denver, for example, Cherry Creek and some of those waterways would serve that purpose?
Yeah. We like to force rivers to do what we want. We build bridges and we build cities, and we force it to go in a certain direction, and which is not good for the river or the ecosystem that thrives around it. But that's the way. I might sound that I'm being facetious about what is done, but the reality is that what else can we do? If we don't control the flow, we're going to have flooding, especially in these areas. Like I don't know of an example in a more humid area where a city is built on an alluvial fan, but these areas are relatively arid. So it doesn't rain as much as you would get. Denver would probably rain much more than here, right? It rains more in Denver. So, but still, what they do is they try to make sure that water flows out of one point to another and control the flow. I don't know about the drainage system exactly in Denver, the creeks that you talked about, but I'm pretty sure that that's what they do.
I have two quick questions.
Yes.
One is, I'm curious about this historic lay of the valley and what it looked like. With grazing, would grazing have kind of channelized some of these alluvial fans so that they no longer move about as much as they once did before?
These alluvial fans, the ones that we saw here in the valley, are debris flow fans. I didn't get into all of that detail.
Mm-hmm.
Debris flow fans are created where you have debris flows. The debris flow is where it rains and the sediments are saturated and it moves down under the action of gravity and it deposits these fans. These are very different fans from the ones that we saw in Tennessee. Those are stream flow fans. So this is probably, when we looked at that, the little video, the video is more representative of what is happening in Tennessee and Mississippi, because those are stream flow fans. The stream gets overwhelmed, it flows over to the side and deposits sediments. These fans here are debris flow fans because it's so steep and it's so arid that it can activate larger boulders and bring that down under the action of gravity. So, did I answer your question?
Yeah.
These are different. I didn't want to get into all of that detail for this talk. Didn't want to confuse you. These are debris flow fans. These are still active. I actually spoke to Sylvia on the phone the other day. I was asking her questions about her dissertation, and she told me that these fans are active. Now, I asked her how old is the oldest debris flow, and she couldn't answer that question because she told me that debris flows are difficult to date, but some of the dates on these fans are 4,000 or 5,000 years old. So definitely those times are when these fans have been definitely that far back they have been depositing sediments. They are still depositing sediments, but not those large debris flows in the recent past.
And my other question has to do with lava. So you gave the example of talus. I always see lava kind of channelizing and then entering these open plains where it kind of creates something like an alluvial fan. What would that be called? This,
Oh, that's just a lava tube that's flowing out of the subsurface, and then is it when it's spreading out?
yeah, like around Albuquerque or Malpais, there's these choke points, and it just seems like there's these big lava fields. And I'm not sure.
Yeah, it could. There are sometimes they have they flow through subterranean tubes, and then when the tube ends, it just flows out. And I'm assuming when you talk about flows, they're more basaltic flows because
I don't know.
one of the reasons why Magoti doesn't sit very high on the surface is because these are basaltic lavas. They can flow very long distances. So the vent is close to the town of Magoti, but the lava flow extends as far north as Capuline. So that's how far the lava extends. This is a stratovolcano because the lava that comes out of this kind of a volcano is more like honey. So it doesn't flow very much. It just heaps up at the surface, which is why it sits higher on the ground in comparison. So I think the lavas that you're talking about are probably basaltic lavas, which flow long distances, and they probably flow in a subterranean tube, and then when the tube ends, it probably spreads out and is able to create some of those flows. Marty?
In the Salt Lake illustration that you used, there's a whole lot of canyons in the Wasatch Range. Would the end of each of those generate its own alluvial fan? And then as they all come together, it's just one big alluvial fan?
Yes, it is. If you look at, let's just. So I think that, first of all, it's very difficult to say exactly what is going on in the subsurface because of all this development that they've done here. If you look at this hillshade, clearly this surface is part of a fan. Maybe they've just shaved off these edges. I'm not sure what they've done when they're building. Maybe because if you look closely, you'll see that the fan abruptly ends here. Fans don't end like that. It would have spread out. So what I think might have happened is the fan probably spread out to at least here. So they've removed sediments to flatten it out to build. And you can see something south of the Conejos River here, there are some smaller fans. There too, they've just shaved off sections of the fan, and they're practicing agriculture, or they've built. So where you have urbanization, it's a little difficult to, unless you have maps, access to maps that are way back in time before the development started, that'll give you a better idea of what the surface looked like. Because clearly, I think that this is a large a bahada, which is, you can see, like you said, Marty, all of these are catchment areas that are depositing sediment to the mountain front, and it probably extended far out in this direction, and they've done some stuff to modify it when they're building. Any other questions?
Have you always been really interested in geology, even since a pretty young age, or when did you decide this was going to be a career path?
I was speaking to Mike before the talk, and that's one of the things that I didn't know anything about geology before I went to college. Someone told me that I could get good jobs in the mining and the petroleum industry. There's a lot of money. So I said, sure, I'll get enrolled in geology. That's the reason why I went to study geology. But as I've been studying geology, I know now that geology has a very wide application, lots of applications other than just mining and petroleum. So to answer your question, I never wanted to be a geologist. I just went there because I thought I could make a lot of money in the mining and the petroleum industry. So, but I think that generally, we were talking about this earlier, that people don't know much about geology. Like I thought that it's mining and petroleum. And Michelle, I was having this conversation with Michelle as well, that more high school students need to know about geology, because there's all the environmental problems that we're having can be understood better if we understand geology. And geology is not just mining and petroleum. There is like hydrogeology, and there is surface water geology, and you've got work done on landslides, debris flows, et cetera, et cetera. So there's a huge bunch stuff, lots of stuff that can be done to as a geologist. Any other questions? Thank you.